If you want to render a 3D scene onto a 2D screen, the basic setup is the following. We imagine a camera in the scene, which projects everything onto a rectangle, representing the screen in front of it. There are a few variations on how to do that. Here, we will follow a straightforward approach, pun intended. We connect a pixel coordinate of the embedded screen with the projection center to form a ray and send it out into the world. We check whether and where it intersects an object. Only afterwards we worry about how light reflects there and color the pixel we started from based on that. Then we do this for all other pixels too. In this video we will focus on the first part, finding the intersection point, and only touch on the lighting issue a little at the very end. I'm Bernhard Werner, and this is a video on the basics of signed distance functions and ray marching. The crucial part in the process just mentioned is that we can actually intersect the ray, which is basically a straight line, with any object we have. For simple shapes like spheres or cylinders, this could be done explicitly. For more complex ones, this is often made possible by modeling them out of small triangles. Then, to check if the line and a triangle intersect is relatively simple and efficient. However, even if we have plenty of little triangles, they will always be a discrete approximation. There's nothing wrong with that per se, but in this video we will now try to model complex objects in a way that uses as little information as possible and give precise intersections. We won't fully achieve that though, and end up with an approach somewhere in between the two cases up on screen. Let's look at this 2D diagram to get a better overview. We still want to shoot a ray out from the camera in the direction of one of the embedded pixels. But we assume that we know nothing about the objects in our scene so far, so let's turn off the lights. Imagine you are standing here at one of the pixels. You would like to know how far you can march along the ray without hitting something, and I will help you. But all I know is where you are, not in which direction you are going. So I tell you the following. One object is 2.2 units away from your position, the next one 5.1 units, and the last one 11.2 units. How far can you go? Just 2.2 units. You can be sure that within a sphere of radius 2.2, there isn't anything you could bump into. Well, right on the border of the sphere there is at least one point of the first object, but if we landed there we would have found the intersection we were looking for. Importantly, on the way to the border of the sphere you won't hit anything. After that we iterate. I again tell you the distances to all objects, you choose the shortest one and walk forward by exactly that amount. Let's turn on the lights again and think about what happens if we do that over and over again. After passing everything vaguely to the sides, you will approach the point where the ray hits something. Unfortunately, unless this part is perpendicular to the ray, you will move at an angle towards it and you will never reach it. There are two ways to think about this. From a purely mathematical perspective, you can just take the limit and do actually infinitely many steps this way until you end at the hit point. For a practical solution, you just stop if the last step you made is small enough, say 0.001 units or so. That means that technically every object found like this is a tiny bit too thick, but that's usually not an issue in practice. We have seen that the so-called ray marching algorithm can find the spots at which the rays connecting the camera and the embedded pixels hit an object. There are two major issues that crop up with that, which I quickly want to address here. Firstly, we have to think about what happens when the ray runs past all objects. With our current algorithm, you would continue to march on using bigger and bigger steps. In this case, you could limit the number of steps you make. If you found nothing after, say, 128 steps, you conclude that the pixel you started from must depict the background of the scene. Another possibility is to check whether the current point you're on is a certain maximum distance away from the camera. You stop if you are past that. In practice, you probably want to combine both ideas. The second issue that can occur is that we may have many objects, and calculating the distance for each of them multiple times might slow everything down, especially if you want to do it in real time, like for example in a video game. To fix this, we can subdivide our space into boxes and record which objects are in which boxes. If we then have a point for which we wish to calculate all the distances, we can limit ourselves to the objects that are in the box the point is in, or in a neighboring box. This subdividing into boxes can be done smarter via so-called Octrees. Instead of explaining that, however, we will now look at how and why the distance information we used is interesting to work with before coming back to actually rendering stuff on screen. You can take any set in the n-dimensional space Rn and define the distance to it from any point like this. You look at all points in the set and calculate their distances to the given point. Then you take the shortest distance and that's it. The individual distances are, at least for our purposes here, computed via Pythagoras theorem. In particular, any point in the set has distance 0 to the set, as its distance to itself is 0. To model objects with it, to be rendered via ray marching, it is more practical to consider the signed distance. The idea here is to calculate the distance not to the set itself, but to its border, which is written with this curved D symbol. We take the distance to the border if the point we are interested in lies outside our shape, but we take the negative distance if it lies inside. And on the border itself, it is 0. Defining the border, the inside and the outside of arbitrary sets can be a bit technical, but in this video we only consider quote-unquote reasonable shapes, so border, inside and outside are what you think they are. There are two reasons why the signed distance is more interesting than the absolute distance. Firstly, it allows us to manipulate and combine shapes in more intriguing ways. We will see that in a few minutes. Secondly, the calculations we will do will often give the signed distance directly instead of the absolute distance. In this video, I will depict these signed distance functions by drawing the border of the shape in question as a white line. Outside and inside, I will use gradients to show how the distance gets larger step by step. Looking at this, you might think they look like topographic maps used for hiking and such, and you'd be right, it's basically the same thing. We will come back to that interpretation later. For now, it's only important to realize that the curves made visual this way are so-called level sets, or isolines, the set of points that are all the same distance away from our shape. In particular, the border itself is the level set of distance 0. The way we define the signed distance here doesn't tell us how to actually calculate it. Checking every point in a given set is of course impractical, and for an arbitrary shape there isn't actually a nice way to compute it. But there are numerous primitive shapes we can calculate the signed distance functions of, and there are ways to combine them into more complex shapes. I will show you a few examples now. For a much larger list, have a look at the website of Inigo Quilez, which is the gold standard of resources on signed distance functions. He also has a fantastic YouTube channel where he shows how to use SDFs for actual modeling. Links to both his sites in the doobly-doo. Since I'm terrible at actual modeling, I will focus on simple shapes to explain the math below. So do check out Inigo's work to see how all this can actually be used in practice. Moreover, I will only show you 2D examples. For many of them, it's straightforward to adapt them for the respective 3D shapes. For all the following calculations, we assume that the point P we want to compute the distance to different shapes for has coordinates x and y. Let's start with the arguably simplest shape, a circle centered at the origin with radius r. We can calculate the distance to the center by the Pythagorean theorem. We then have to offset it by the radius. This expression might look quite familiar to you. It is very similar to the more common circle equation x squared plus y squared minus radius squared equals 0. And this is a good opportunity to stress the following point. There are infinitely many functions that are 0 if and only if the input lies on the circle. But we want more. We want every function value to have a particular meaning, namely describing the distance to the object. If we were only interested in describing the border, there would be many more ways to do so. Let's go to a different shape. A straight line. If we assume that it is given by a point Q on it and a normal vector n of length 1, then the distance is given by this linear formula here using the scalar product. Setting this expression to 0 gives the so-called Hessian normal form of the line. In contrast to the circle, this common way of describing a line is already the distance, at least as long as the normal vector is actually of length 1. Note that due to the way we define signed distance functions, this is technically not describing the line itself, but the half space bounded by it. For the actual line, we would have to take the absolute value of this function. Next, a class of objects ubiquitous in graphics programming, line segments. If P is beyond the endpoints E and F, the distance we are looking for is the distance to the closer endpoint. If it hovers somewhere over the middle of the segment, we need to find the length of the perpendicular vector that connects the point to the segment. For this case, we could use the same formula as for lines, but with a small algebraic detour, we can also find out in which of the 3 cases we are along the way. We calculate this value lambda here via the scalar product. It will run from 0 to 1 as the projection point of P onto the segment runs from E to F. In this case, we get the desired perpendicular vector v as this linear combination here, and the actual distance as its length. Moreover, lambda will be below 0 if p moves beyond e, and bigger than 1 if p moves beyond f. So this value lambda not only allows us to determine the distance if we are in the middle case, it can also help distinguish between the cases. Instead of doing a distinction by cases, however, we can do something clever to combine the three cases. When the fraction of scalar products is negative, we are beyond the endpoint e, and we need to take the length of p minus e. If we look at the definition of v, we get that vector if lambda is 0. So if we can set lambda to 0 if the fraction is negative, we would have incorporated the beyond e case into this one. And we can do that by setting lambda to the maximum of the fraction in 0. If the fraction is bigger than 1, we are beyond f, and we would like v to be exactly p minus f, which we get if lambda is exactly 1. Similarly to before, we can achieve this by taking the minimum of our value and 1. This way, the resulting vector v will always give the distance no matter in which case we are. And we get a relatively simple formula for the SDF of a line segment. As a final example for now, I'll show you the signed distance function for a so-called axis parallel rectangle centered at the origin. That is, a rectangle where the sides are perfectly vertical and horizontal, respectively. Here we can use symmetry and mirror everything into the first quadrant, i.e. we replace our point P by a point Q by taking the absolute values of the coordinates of P. We assume that the size of the box is given by the position of the top right corner, which we call B. Then we can express the distance of Q to the box by looking at the vector v from B to Q. Firstly, the point Q could lie somewhere to the top right of B. Then B is actually the closest point of the rectangle, so we can just take the length of v. Secondly, Q could be right above the box, and we would need to project down again, similar to the line segment from before. But since the rectangle is parallel to the axis, the distance is just the y-coordinate of the vector v. And the x-coordinate of v tells us when we actually are in this case, because then it points to the left, and so the x-coordinate must be negative. We can now use this fact that the coordinates of v play entirely different roles and combine cases again. We can build a new vector u by rounding the x-coordinate of v up to 0 if it is negative. When v points to the left, its tip is effectively pushed right until it's vertical. Then its y-coordinate coincides with its length, and that is the length we want. And if we are in the top right again, u will be the same as v, since its x-coordinate is positive and we get the same as before. Thirdly, the point Q could be somewhere to the right of the rectangle. We can use the same argument as just now and shift v upwards by taking the maximum of the y-coordinate of v and 0. That means as long as the point Q is outside the box, we can look at the vector v, round its coordinates up to 0 if they are negative, and take its length as a single formula for all three cases. Inside the rectangle, the coordinates of v themselves represent the distances to the edges, so we can just take the smaller one. Well, the bigger one, since they are both negative, and we want the distance to be negative on the inside. All that's left is to find out whether an arbitrary point Q actually does lie on the outside or inside. Note that the outside distance we computed is always positive, and the inside distance is negative if and only if the point lies on the inside. That allows us to take the minimum of the inside distance in 0 to actually limit it to negative numbers. But now, the result that's coming from the wrong case will just be 0. That means we can just add them together and don't need to worry at all which case is the currently correct one. Long story short, we get the SDF of an axis parallel rectangle without ever having to check where points lie in relation to the rectangle. There are many more SDFs you can compute with a bit of effort, or you do the same as I and everyone else and check Inigo Quilez website. There you find moons, hearts, crosses and many more. In order for all those SDFs to be actually useful, we need to be able to transform them. For example, we only considered circles around the origin, but we might want to move them somewhere else. We only have the SDF for axis parallel rectangles, but we probably want to be able to rotate them. Take this set here and assume we know its signed distance function d. Then we apply a rigid transformation to it, which is a combination of a translation and rotation. That means that the shape itself doesn't change, just its position and orientation. If we then take this point here, for example, and try to find its distance to the object, we can move everything back to the original position, i.e. we apply the inverse of f. Since these rigid transformations don't change distances, we can evaluate the SDF we have, namely d, at this pre-image of p under f. Since that works for every point, the signed distance function of the transformed object is the original SDF d concatenated with the inverse of f. This way, we can move objects for which we know the SDF freely around. Another way to change SDFs is by making the shapes rounder. Take this rectangle for example. If you subtract a small number r from its signed distance function, the corners get rounded off. Depending on your use case, you might have to compensate for the change in size though. As another example, if you start with a line segment and subtract a number, it turns into this capsule-like shape. This works for any SDF, but is most relevant and interesting for objects with actual corners. There are more ways to manipulate individual signed distance functions, especially in 3D. Next, however, I want to talk about how to combine them. Take these objects here with SDFs dA and dB. We might be interested in the SDF of their union. Consider an arbitrary point. One of the two parts is closer than the other, so that must be the distance to their union too. That means the SDF of the union is just a minimum over the given functions. Except it isn't. If you look at the inside, you might see that the isolines don't ripple inwards properly. Take this point here for example, and let's see where the boundaries of our starting shapes were. The closest points on them to the yellow one are to the bottom left and right above, respectively. The closest point of the boundary of the union is this corner here, however, and it is farther away than the other two, which are used to calculate the combined SDF. Hence, we get a distance that is too small, or here too large, since we are in the inside and everything is multiplied by -1 there. We could just ignore this, because in the end we want to render 3D objects we see from outside. But unsurprisingly, the next thing to look at is the intersection of our two shapes. With a similar argument as before, we can get it by taking the maximum of the given signed distances. And now the outside is slightly wrong, for very much the same reason. You can see that if you compare the top left and top right corners of the shape. Depending on your use case, it might not be a big issue. For ray marching alone, for example, it mostly means that we need more iterations. The correct SDF for this object would look like this. Look close at the ridge coming out of the top left corner. But in general, just taking the maximum will be wrong, and there's no way to fix it for arbitrary signed distance functions. In practice, there are ways to work around this problem. In the example on screen, I intersected the circle not with the rectangle we started with, but with this pentagon here. But that's more of an artistic approach. You think about the shape you want to end up with, and then you look for a way to get it. From the math standpoint, it would be nice if you could properly intersect any two shapes via the maximum. Alas, we can't. Moving on to the last operation, we can cut out one shape from another. If we take the negative of the circle SDF, we basically say that the inside should be interpreted as the outside and vice versa. If we now intersect it with the rectangle, we cut away the part where the original shapes overlapped. And here, the level sets clearly look wrong. There's more to say about these three operations. Moreover, they aren't the only ways how to combine signed distance functions. And we have seen that one needs a clear plan which shape one wants to end up with to use them properly. But I hope you can now imagine how it might be possible for complex shapes to be built from simple ones using SDFs. Instead of talking more about the technical aspects of these functions, I now want to go back to our initial problem of rendering 3D objects. As explained at the beginning of the video, we imagined a screen to be embedded in our scene. We send out a ray from the camera towards every pixel and intersect the ray with several objects using ray marching. Based on the point we hit, we have to decide on a color for the pixel. Let's start by making a pixel white if we hit something and black if we didn't. If we now let the camera rotate, you might already be able to recognize the objects we saw at the start. A capsule, a frustum and a cube. Currently they look very flat though. To make them look more three-dimensional, we still calculate the hit point with an object in the direction of every pixel, but then we calculate the distance of said point to the camera. We color the pixel white if the point is less than 60 units in front of the camera, and we color it black if the hit point is more than 90 units away. In between, we interpolate with gray values. The result already looks much nicer. We could tweak this a bit, but this is basically the full information of how our objects look like seen from the camera. At least if we are only interested in the pure geometric information of the shapes. But, as I mentioned in the beginning, we could also take a couple of light sources into account. Lighting models are a big topic, however, so I don't want to actually talk about them here. There's one bit of information, however, we need for lighting calculations that we can extract from our signed distance functions, and I want to show you how. When light reflects off a surface, it happens in two major ways. For shallow angles, the light reflects fairly cleanly in the opposite direction it came from. It spreads only a little, depending on how smooth the surface is. Or, for steeper angles, it scatters in all possible directions, but mostly upwards. The first is called specular reflection, the second one diffuse reflection. To model either of them, we require the normal vector of the surface. That is the direction that points straight up from the surface at the point the light hits. Let's see how we can get this vector for our signed distance functions. For the 2D case, they are functions that take a point in the plane and give back a single real number. So their graph can be depicted as a surface in 3D space, where the x and y coordinates represent the input and the z coordinate the output. Recall that a set of points that all map to the same value is called a level set. We can visualize it here by intersecting the graph of the function with a horizontal plane. If it sits at z equal 11, for example, the curve in which it intersects the graph represents all points that are mapped to 11. And we already briefly talked about how for signed distance functions, the border of the defining set is just a level set at height 0. For all reasonably nice functions, the direction perpendicular to any level set is the direction of steepest ascent. i.e., if you imagine the graph to be a hill you walk on, you can walk along a constant height, and if you turn 90 degrees, you will face the direction where the hillside is the steepest. Maybe you've experienced that yourself on an actual hill. If you take this point here on the second visible level set, for example, we can move it around, and the upward direction of the quote-unquote hill will always be perpendicular to the level set at that point. And if we go back to the flat depiction of our SDF, we see that this direction is still perpendicular to it. The important fact for us now is that this direction coincides with the gradient of the function. It is defined as the rate of change in the x and y direction. We walk a tiny distance epsilon in the positive x direction and the same in the opposite direction, and compare the differences in the function values relative to the total distance walked, i.e. we divide by 2 epsilon. For the y direction we do the same. In math, we would now need to take the limit of this as epsilon approaches 0. For coding, we can simply take a really small value for epsilon and plug it in. Note that in practice it is often more efficient to explicitly calculate the gradient for the primitive SDFs you want to use and then alter and combine them similarly as to how the SDFs themselves were altered and combined. But this numerical approximation here always works. To wrap up the video, I will, as I already announced, skip all explanations of the concrete lighting model and just show you the result. But I'll link to the Wikipedia page of the model I used in the description. Here, we just need to know that it needs the normal vectors of the objects, and we just saw, at least in 2D, how we can obtain them from the SDFs. In 3D, the calculations are analogous. Here's the version we had before. If we color the background and give each object a bit of base color due to ambient light, we get this starting image. Adding a red light that shines towards the right, a green light that shines to the left, and a blue one that shines downwards will result in this render of our scene. There are many more applications of signed distance functions. One you have seen throughout the video is to depict shapes in 2D. Another application is rendering fonts, and there is a link to a blog post on this topic in the doobly-doo. Lastly, you can use SDFs for collision detection in, for example, physics simulation too. But the rendering of 3D scenes via ray marching might be the most famous application. With that, thank you for watching, and until next time.